Alrighty, friends. We're going to power through Unit 3, Lesson 1, the part that we didn't get to do yesterday. Definitely through Unit 2, or Lesson 2, and we might even take a little dip into Lesson 3 because Lesson 2 is pretty short. So have your workbook open, pause when you need to, and check your answers on Google Classroom when you are finished. If you have any extra time, practice or prep your help sheet for our test later this week. So I'm here on page 7. We're looking at 1.3, the power of 0. Yesterday we took care of name that power in class, and so we're looking at all of those rules and properties of exponents. Now this one is really just using one property over and over and over again in here. I see a lot of this division going on. And so when I look at this, I'm going to be using that rule that talks about b to the m over b to the n, and it tells us we will just subtract the two exponents to come up with our answer. We shouldn't need a calculator to do it, but it is a self-checking activity in case you want to check that you have your work done, but it's also on Classroom, filled in and ready to go. So for each of these, I see that here they just simply took that first one and did the subtraction already to begin with. So if we think about it in the meantime, here's the step that they skipped. 2 to the 5 minus 1 gives us 2 to the 4th power, and that means 2 times 2 times 2 times 2, and so we can look at it that way. Another way to think of these powers and exponents is that we can actually multiply it out how many times we see and then cancel out whatever we can. So if I have 2 to the 5th, that's 2 times 2 times 2 times 2 times 2, divided by 2 squared, that would be 2 times 2. And when I see what I can cancel out, I can cancel out 2 2's like that, and another set of 2's on top and bottom, and what I have left is 2 to the 3rd power. So even if you can't remember this rule specifically, you certainly could do something like this to remind you of what that rule is or to see what your result is. So now we have 2 to the 3rd power. 2 times 2 is 4 times 2 is 8. That gives us our value. I'm going to keep on going this way because knowing this rule, it's really nice and easy. So 2 to the 5 minus 3 gives us 2 to the 2nd power, which is 4. 2 to the 5 minus 4 is just 2 to the 1st power, which is 2. And maybe you're already noticing the pattern that's going on here. Back to our first unit where we were talking about sequences, each time it's multiplying by 2, so it has a growth factor of 2. Here we would have 2 to the 0th power, and anything to the 0 power is 1. Now again, we see that same pattern happening. So if we're multiplying by 2 or dividing by 2, if we're going down like this. So that should tell you if we're dividing by 2 each time as we work down in this chart, our next value should be 1/2. But if we really think about it this way, we have 2 to the 5 minus 6, which is 2 to the negative 1. And we also had a rule that told us that if we have anything to a negative power, that's the same as 1 over the base to that power. So this would be the same as 1 over 2 to the 1st power, or 1/2. And last but not least in this table, we're looking at something like 2 to the 5 minus 7, or 2 to the negative 2 power, using this idea that a negative exponent kicks it to the denominator, means we have 1 over 2 squared, which would be 1 over 4. Again, you can always write these things out if you really have to prove to yourself what these values would be. 1, 2, 3, 4, 5, 6, 7. So I have 2 to the 5th over 2 to the 7th. And so you can see that we have 1 over 2 squared. That would get us that 1/4. So keeping and thinking here, the value of 5 to the 0, well, we have a rule that says anything to the 0 power, always, 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 anything to the 0 power is 1. And so this idea again of using these exponents or this rule that we have right here, I see a negative exponent. So 3 to the negative 1 is the same as 1 over 3 to the first power, which is the same as 1/3, or 1 over 3. You could also use the subtraction rule, this guy up here, in reverse, down here. So if I'm thinking about what I could subtract, I could take this idea, if I need to get to a negative number, like this next one, 7 to the negative 3rd, and I could write something like 2 exponents that, when I subtracted them, would end with a negative 3. So if I had something like 1 here, and the 4th power down here, those would subtract. 1 minus 4 is negative 3. Or I could write even a simpler one, 7 to the 0 over 7 to the 3rd. That would be 0 minus 3, or simply looking at what we had in this rule up here, using it down here. Anything to the 0 power is 1. That 7 to the 3rd would be in the denominator. So then we're looking at something like 7 times 7 times 7, which I'm sure you all have memorized, that 7 to the 3rd power is, of course, 343. I'm sure you knew that right off the top of your head. I didn't. I used my calculator. So that is all set for us. Okay. Explain why the argument used to assign a value to the expression of 2 to the 0 doesn't apply when we have 0 to the 0. If we actually do that, if we have 0 raised to the 0 power, you're actually going to get a domain error, this thing that's saying you can't do that, right? So I typed in 0 to the 0 power and I got an error. And so when we think about it, it's because of this exact reason, this idea that if we were to write it as a fractional exponent like this, we would have something like 0 to the 3rd over 0 to the 3rd. And we can't have 0 in a denominator. That can't happen. So it just doesn't make sense. Let's flip on over, and this one I'm just going to get you started and ask you to finish it off, because it's simply matching some values, sorting expressions into groups. They're telling us what we have. Oops, sorry about that. Just want to see how long I was working. So, sorting some values and seeing what they have in common. So maybe you're looking at a couple of these things, like I see this 2 to the negative 4th is the first one that's in there. We just had a rule on the previous page we looked at that told us any negative exponent is going to kick it down to the denominator. So what do you know? These two actually have the same value. Now there might be something else that also has the same value, so I'd have to be looking at other ideas. But when we have 2 to the 4th, what those would be, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. So these items equal 1/16. Alright, and you'll see the answer key written like this. That the things that share the same value of 1/16 is 2 to the negative 4 and 1 to the 2 to the 4th power, 1 over 2 to the 4th power. So those two have that same value. Now remember, there is a difference between like this negative 4 squared and this negative 4 squared. If it's in parentheses like this, this is saying negative 4 times negative 4, and a negative times a negative is a positive number. So negative 4 squared, negative times negative is positive, 4 times 4 is 16. If you're not sure, double check your calculator. This is actually why we get different answers when we have negative 4 squared in the calculator compared to negative 4 squared, which gives us negative 16. Because what this is telling us, our PEMDAS, or order of operations, tells us we do exponents before we multiply to a negative. So this value equals negative 16. So we're going to have some values that equal 16, some values on this page that equal negative 16. Alright, so sort through these things, work through them. Some of these you'll have to do some of the math using some of our other properties. This one where we would be adding exponents. So this is looking like 2 to the negative 4. Well, that's looking an awful lot like this guy up here that was already 2 to the negative 4 that we already said is here in the 1/16 category. So 2 to the negative 7th times 2 to the 3rd would also be a value of 1/16. Keep on doing this. Hit pause right now and work through the rest of these of where you would sort these things out so that they are in groups. And remember, some of them may not have a match and some may have more than one match. So a way we can do it is like this. Hit pause, finish that up. Notice at the bottom of the lesson 1 summary, there's all of those same rules that we're using that we already had you write in. We learn sometimes by writing. So I'm going to start on to lesson 2. In our warm-up, it's just asking us to recall how we can find the area of a square, in this case square ABCD. And we could certainly use some ideas like Pythagorean theorem. It's such a commonly used theorem that you will definitely see it on the SAT test. I want you to think of me when you see it because it will definitely be on there. If you don't remember the Pythagorean theorem, we have two sides of a triangle that we call A and B, and the longest side, the one opposite the right angle, that we call length C. And A squared plus B squared equals C squared. So in this case, we would have our side A is 2 squared plus side B 3 squared equals our unknown C squared. 2 times 2 is 4, 3 times 3 is 9. And to get rid of that squared, we of course need to take the square root. So each of these side lengths, because each of the sides are the same, each of these inner sides of this square ABCD would be the square root of 13. Now I haven't quite answered the question yet because it's asking me what is the area of square ABCD. And area for a square is length times width, or square root of 13 times square root of 13. Well, if I have the same thing squared and multiplying each other, what I have is the square root of 13 squared, and so those two things are going to cancel each other out. And once we see that the square root of 13 squared cancels each other out, we can find that the area of this is 13. Now we're using this idea because on the next page it's going to ask us all kinds of squares and their side lengths. And remember how these things are working. In fact, this is the exact definition of a square root. That if we know the area of a square, in this case square C has 1, 2, 3, 4, an area of 4 squares, the side length would have to be the square root of 4, which means 2. It'd have to be 2 times 2. So we start to see why this thing is called square root. Anyways, it's because it helps us find the area of a square, or if we know the area of the square, to find the root sides that make that area. So I'm going to fill in this chart. Filling in the easy ones first. We already know this is a 1 by 1 square here, and 1 times 1 is 1. It's 1 square. Now, B, D, and E are a little bit different because they're not on a flat edge. So we could work a couple different ways. Here, one way to think about this is that this is half of a square, and this is half of a square, so that is 1 square. And here's another half of a square and another half of a square. So this figure B has an area of 2 squares when I kind of swing that over and reassemble it into a full square. So our side length is going to be square root 2, which you may also remember from geometry when we did something with these right triangles that had a length of 1, 1, and the hypotenuse then was the square root of 2. So we have square root 2, and those two squares of 2 would multiply to an area of 2. We can think about the same thing here in part D. So I have one square that sits right here in the middle, the square that's split between these two, the square that is split here. Are you ahead of me in seeing that it's 1, 2, 3, 4, 5 squares? And when you start seeing this, I bet you already know what E is going to be. But our side length is now going to be a square root of 5. We could also think of it as, here's a side, a triangle off to the side here, where this is 2, and this is 1, and A squared plus B squared equals C squared. 1 times 1 is 1, 2 times 2 is 4. So maybe you're already seeing that each length here is going to be the square root of 5. Thinking of the same way here, we have a 2 by 2 triangle on the outside. A squared plus B squared equals C squared. 4 plus 4 equals C squared. There's each of our side lengths. And our area then would be square root of 8 times square root of 8, or square root of 8 squared, which equals 8 squares going on. So here's 1, 2, 3, 4, 5, 6, 7, 8 squares. Right, and so we can also find some other areas that are in between, so we can even use this relationship between area and side length to now figure this part out. So if our area is 9 square units, side length would have to be the square root of 9, which in my book is 3. Now you might be asking, why don't I also write -3 here? Because I know we've talked about that a lot in class already. And I'm like, ooh, what's the square root of 9? And you say 3. And then I say, ooh, what's the other square root of 9? And you say -3. Well, when we're looking at this, we would actually be having some values here where we would not make sense to have a negative side length. You just wouldn't do that. So that's why I'm only writing the positive values. So if I keep on thinking about this, it would be the square root of 23. The square root of 89. Now when we're thinking about what these might be as decimals, it's going to come up later where we're going to have to start estimating what these things might be. But maybe you're just thinking, I could use a calculator to solve some of this. You certainly can. Any kind of calculator is going to work to find that square root of, oops, sorry, you can't see that, square root of 23. And we're going to get about 4.79. So about 4.8. So to get from a known area to a side length, we just had to take the square root. To go the opposite direction, 3 squared gets us 9. So to find area, we would need 4 squared, and that equals 4 times 4 is 16. Or 6.4 squared, which equals, dear calculator, 40.96. Moving on over to the cubes. Cubes are simply squares in 3 dimensions, where each of them has the exact same length. So the cubes that we're working with start as squares and then move into the 3rd dimension, which is also a value of x. So this is why we call it cubing things, right? When we have something to the 3rd power, it's because cubes have 3 dimensions, all the same size, the same length. So if a cube has an edge length of 3 units, the volume of the cube is length times width times height, also written more simply as 3 to the 3rd power. 3 times 3 is 9, times 3 is 27. I think you've got this part from now. So go ahead and finish off these next couple ones here, thinking that cubes just mean we're taking it to the 3rd power, right? Now I already know that the volume of 7 units better be between these two, because 7 is between 4 and 8. Good to go. So we're already seeing when we're going to use some of these values. Here's our last idea here in lesson 2, which is perfect because we still have some time to kick on to lesson 3 to at least get started. It's going to ask us to start putting some of these in order. You may remember this question from your Unit 3 check for readiness. And some of you are like, I don't really know how to do this. The cube root, some of these things, I'm just like, I don't really know. But notice that here, we're just looking to estimate where it would fall between which 2 numbers. So it's not asking us to solve it out to a decimal, right? But it's saying, hey, if we want to find the cube root, that's how we say that word, if it's got that 3 in front of it, that means we need to find the cube root of something. And we could put any number in front there. It just means that I need to find 3 numbers, 3 of the same numbers, that multiply together to get to 1200. Right? And so if we had a 5th root of something, that means I'm looking for a number times itself 5 times to get to whatever is under that radical symbol. So you're going to hear me start using this term for this symbol. It's called the radical. This is telling us the root, and the radicand is the thing underneath it like that. All right. But we're trying to figure out what numbers this would be between. So if I think about a number that's going to be multiplied by itself 3 times to get to 5. Well, if I think about 1 to the 3rd power is 1. And if I think about 2 to the 3rd power, well, 2 times 2 is 4 times 2 is 8. Now 5 is somewhere between 1 and 8. So the 3rd root of 5 is somewhere between 1 and 2. So this is asking us just to put this categories of where these things fit and what numbers they are between. All right. So what we're really starting to think of here, let me get my highlighter to show you. We're looking at what base number here that the root lies between. So the 3rd root lies somewhere between 1 and 2 in this case. Now we already did 2 to the 3rd power and found 8. I bet you 3 to the 3rd is going to be much too big to get to 10, right? So 2 to the 3rd power is 8. 3 to the 3rd power is 27. Maybe you remember that because we just saw it on the previous page. And so because 10 is between 8 and 27, That means the third root of 10 is between 2 and 3. Keep on thinking about this, right? We're going to see what else we can do here with the third root of 50. I'm really just kind of now thinking about all of these things to the third power. And when I'm taking 4 to the third power, I'm getting 64. 50 is definitely between 3 and 4, or between 27 and 64. So I know my third root is going to be between 3 and 4. Go ahead and finish off the rest of this. If you really want to check yourself, you can certainly use a calculator to do that. If you're using one of these nifty little guys here, finding that third root, you might see it right here, where it's got an X in front of the root symbol. For both types of calculators, if you want to take anything higher than a square root, because this one's got a square root going right here, but if you want something higher than a square root, like a third root, you have to type the 3 in first. And then we'll hit that button here to show us the root symbol. We're trying the third root of like 100. Looks like our next question. Well, that's going to be somewhere between 4 and 5, because 4.6 lands between 4 and 5. So in this calculator, we use that button right here that has X in front of the square root symbol, the radical. Here, you will find it on your TI-84s and such. Now that I've put the first number in first, I'm going to go to the math button. So when I hit the math button, there is that same idea. And actually this also does the third root of something. But if I go down to number 5, I can find any number root that I want to at all. 3rd, 5th, 10th, 100th, whatever it might be. And if I'm looking for the third root of 500, we can calculate that and see that it's really close to 8, but not quite there. So it's between 7 and 8. So this last answer should be between 7 and 8, the third root of 500. So this is helping us kind of get a decimal estimate of what it's going to be between. So there's our lesson 2. Final concept, lesson 3. Exponents that are unit fractions. Now you're probably thinking, oh my gosh, I thought we were done with fractions, we're out of the radical unit. But we can have fractions like 1/2 and 1/3. That's no big deal, right? You're going to see actually really how nicely this works. Finding a solution to each equation, we've already seen kind of how we can do square roots and use that to do opposite operations of squares. And so we would find that x equals 5, because 5 times 5 is 25. And our other square root of 25, -5. But if we start having something like z squared equals 7, same kind of idea. Z is going to equal the square root of 7. Now, 2 squared is 4, 3 squared is 9, so it's somewhere between 2 and 3. I don't know exactly what it is, but I could estimate it somewhere in there. And we can do the same thing with cubes. We just put a 3 in front and find that we're cubing it, finding the cube root of something like 8. So I need a number times itself 3 times to get to 8. And when I think about what that number might be, I see that 2 times 2 times 2, 2 times 2 is 4, times 2 is 8, is that number. So the same number times itself 3 times, that tells me what a cubed is. So y actually has to equal 2. So sometimes they're nice, straightforward whole digits, integers that we could have. Other times we're just going to leave it as the cube root of 19, because the cube root of 19 is somewhere between 2 and 3. That's all that I know, because I know the cube root of 2 is 8. The cube root of 3 is 27. Again, we just saw that a couple pages ago. So it'll be between 2 and 3. But I don't know exactly what it is. So these kinds of fractions, right? Now we can start throwing some stuff where we're like, wait a second. I wonder what 9 to the 1/2 means. We saw before when we had some things in that was a negative number, it was kicking it down to the denominator of a fraction. That is not the case here, right? We saw something before where we had like 2 to the negative 3rd power was the same as 1 over 2 to the positive 3, the positive 3rd power. This is different though. This has the exponent is where the fraction is showing up. So it's going to be something else, right? And so 9 squared is 9 times 9. 9 to the 1st power is 9. 9 to the 0 power is 1. So notice how many times we're like multiplying 9s or like dividing by 9s. And maybe you're already starting to see this. That we had 9 squared was 2 9s multiplied together. Then we had just 1 9, so 9 times 9 divided by 9. Divided by 9 gets us to 1. And so if I want to keep on going, maybe we're going to be looking at something like that. Alright, so this one asks you to first graph for 9 to the x power. Right? And so then we're going to use it to kind of get an estimate. So I'm going to skip every other line here and work it from there. And setting up a little table going on here. So if I have 9 to the 0 power, my output is 1. So 0 power, my output is 1. I'm not even going to graph the x. I'm going to get some big numbers here. 9 to the 1st power is 9. 9 to the 2nd power, 81. 9 to the 3rd power. Now we're already starting to get into some pretty giant numbers. Because 9 to the 3rd power is 729. So I'm actually not even going to go that high up here. If I just graph my first two, 9 to the 0, to the 1, and to the 2, I know I'm going to be finding the 1/2 is going to be something in between these two. And what we're actually going to find here, let's go ahead and graph these. Let's set up our graph on a scale so that we get up to 100, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Can we go by 5s? 5, 10, 15, 20, 25, 30, 30, 40, 50, 55, 60, 65, 70, 75, 80, 85. Yep, we can count by 5s. And so when I plugged in 0, I got 1. I plugged in 1, I got out 9. I plugged in 2, I got out 81. Now you see why they're called exponentials. Look at how high they grow so quickly. Graph looks kind of like that. So if we're looking for 9 to the 1/2 power, that would be this line right here. And that 1/2 is not quite at 1 and not at 5. It's kind of in the middle there. And so to estimate from the graph, we'd only know that it's somewhere between 1 and 5. So I'm going to estimate that 9 to the 1/2 power equals somewhere around about, I don't know, maybe 3, maybe 4. I'm going to say 3. Using some of these properties, if you remember before when we said we had the same base, we could add those exponents. Nine to the 1/2 times 9 to the 1/2 is the same as 9 to the 1st. And 9 to the 1st equals 9. So to find 9 to the 1/2, what that's saying, let's see, how else can we go about this? 9 to the 1/2, really what we're going to find is this fractional exponent is the same as 9 to the 1st, the numerator, square root. Now I write it this way because this is going to come up a little bit later in actually lesson 4, where they're going to start changing those numerators. But putting 9 to the 1/2 power, another way to look at that is to actually just type in the calculator. 9 raised to the 0.5 power, or 9 raised to the 1/2 power, gets us 3. So whatever's in that denominator is now going to be out in front of our radical symbol. It's going to tell us how many roots we're looking for. Kind of cool. So when I see something over here like this, now it's going to ask me to get that same idea. I'm wondering about 3 to the 1/2 power. So go ahead and graph some ideas about 3 to the 1/2 power. Again, let's set it up in a way that we're doing some input-output tables. So you've got 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. And let's even spread out our x coordinates so it's even a little bit bigger. Because 3 to the 0 power is 1, 3, 9, 27. So, 2, 3. Let's just make each one of them a quarter. 2, 1, 2, 3. 3. With a smaller base like 3, we can use some bigger numbers here. I'm going to use my same scale of by 5s going on my y-axis. Oop, that's 50, not 15. And now we can graph it. 3 to the 0 power was 1. 3 to the 1st power was 3. 3 to the 2nd power is 9, not quite up at 10. 3 to the 3rd power is up at 27. 3 to the 4th power was way up here at 81. Sketching a graph can again help us estimate. What's that dot? And now if I'm looking for 3 to the 1/2 power, I'm looking here because that's where our 1/2 value is. I'm estimating it right here. It's somewhere between 1 and 3. It looks a lot closer to the 1 than it does up here to the 3. So I'm going to guess it's probably at like 1.8-ish. I don't really quite know. Well, when we take that value and square it, that number times itself. 3 to the 1/2 power squared. We learned in one of our rules that we could multiply those together. 3 to the 1/2 squared is the same as that would be, well, it's 3 to the 1st power, right? Because 1/2 times 2 is 1. So we found out that that equals 3. And it does. It looks like a root going on here, right? Because we're taking inside the parentheses whatever's in that denominator and putting it out in front of the radical symbol. And then here they're squaring it, right? And again, this idea that a square root squared cancels each other out and leaves us with the same value. So our big idea is that if we have anything to a fractional exponent, like that, it just means we're finding that root of b. Add this idea right here to your thinking. This is our big idea from lesson 3. We're at about 40 minutes of video time, so it looks like it's a good time for me to kind of wrap this idea up. But we can get some extra practice going on here with 3-3 and 3-4. Pretty quickly we can just be writing these as the square root of 25, which we can do. We can find the square root of 25. It's 5 and negative 5. Square root of 15. So I have to find some numbers that are going to multiply to get together to get 15. Two numbers are going to multiply together, so it's got to be, let's see, 3 times 3 is 9, 4 times 4 is 16, so it's got to be 3 point something. Closer to 4, because 15 is closer to 16 than it is to 9, right? Third root of 8. 2. Third root of 2 is going to be 1 point something going on there. Alright? So this is simply asking us to find some exact values. We would use our calculator to go right on out and find it. But really, I mean, you know, we could start using all kinds of different math. 3 times 3 is 9. So we've gotten there. And what we have left is 6. So now I need to find the root of 6. Yep. If we had something like 3.8, we could certainly do some math like that. But yeah, it's a-okay to go here and be saying, hey, what is the square root of something like 15? And there's that 3.87. What is the third root of 2? 1.26. Little matching going on here. Some of them are worked out, some of them are here. Remember that a negative is what kicks it down to the denominator, so if I think about something like 7 to the negative 1/2, that's telling me first of all that I need to have it kicked down to a denominator with a positive exponent. And now I'm going to apply this idea about it being a square root of 7. Remember, if there's no number written out front, we assume it's a square, so we assume it's a 2. So if I have 1 over the square root of 7, that's telling me this guy is going to match right here. Anything to the 0 power is 1. Okay. So match this up, check the classroom for those answers. That's lessons 1, 2, and 3. Holy smokes, you guys got this.